All right, let's get started. I found issues. There might be a bug for this sort of like a lecture and lab structure because now the TAs will explain exactly everything that needed to be explained for this class, right? Some of the TAs will explain more, some of them probably will not. So good news is I found a solution for this issue for very big sections, like 4 sections for this class. So I will explain the questions. I know this is due tonight, right? So in-lab questions. I'm going to explain every single question. During the first section, I think on Thursday, I was able to go through like 10 or 15 of them. But like what I said, I'm not able to stay for the whole day until like 7:50 or 8:50. I forgot the time. 7:50. Too much. So Monday, how long I work on Monday? I know you guys work or study sometimes pretty long as well for the days. But Monday, I usually wake up on Monday, Wednesday, Friday. I wake up pretty early for working out. So I usually wake up at 5 a.m. and.
What's your split?
What do you mean split?
Like, do you do like an Arnold split, like back in chest, or?
Oh, I do. Yeah, pretty much. I don't know the names of here, abs, leg. I run first. I run 5 kilo every morning.
Full body every day?
Yeah, but I only 2 groups, not 3 groups. I used to do 3 groups, but not just 2 groups. Since I run for 30 minutes, I can do 5 kilo. And then I get sweated, so which is the most effective. I highly recommend running. I also do swimming. A lot of people say swimming the best sport. Actually, it's not. Even though it's really good. I know it's really good. I swim. I used to swim. I couldn't swim really well, but 3 years ago I started swimming. What I can do now is about 2 kilo, 40 round trips to the 25-meter swimming pool. So I can do 1 kilo no break. But mixed. So it's one lap for freestyle and breaststroke for another. I couldn't do like freestyle always, but I can do breaststroke for all of them. I have to do, if I do freestyle, I have to do breaststroke for another when I come back. So anyway, I can do like 1 kilo mixed, no break, and then I take a break and then do another kilo, so 2 kilos. But I can see, yeah. What's that?
Do you lift at the rec or where do you lift?
Where do you lift?
At the rec center? Or
oh yeah, rec center.
Rec center, okay.
Go to yeah. Anyway, so I don't want to take too much time to talk about that. But running, I think for me is the best. But for some of you probably is not. But swimming is good, but not as effective as running because you guys in the future will be super busy. You'll be engineered like me, right? On Monday, I can let you know I only have like 1.5 hours to work out. After that 1.5 hours in the morning, I have to work for like 14 hours for the whole day. So I teach 2 classes. So office hours in the morning from 8 to 9:30. So I finished working out probably around 7:10, and then I come to school. I usually take my breakfast in office, and then office hours start at 8 a.m. And then 9:30, I finish my office hour, and then 10 will be my Circuit 1 class. I teach Circuit 1 at 10 and come back sometimes for lunch. Sometimes I don't even eat lunch. Like today I didn't even eat lunch. Then 1 p.m. will be the class, right? But on Monday after this, I will like work on something else, prepare for lectures and all the notes and everything. I don't grade, which is great. And 6 p.m. will be the PCB class for like 3 hours. So after that one will be somewhere around, I think 8:50 will be the end of the class, of the PCB class. 8:50 p.m. And sometimes students also have questions. I will probably end that day at around like 9:10. Then I go back home. Will be like 9:30. So if you look at the time, from 5 a.m. I wake up to like 9:30. Super long day. If I don't work out, I will die for Monday. But after 2 hours working out, I feel like just full of energy, so I can deal with that kind of thing. So in the future, you guys will be super busy. Just take like 1.5 hours sometimes, do whatever you are good at. Can be swimming, playing basketball, whatever, running, or swimming, whatever, right? You don't have much time. Only 1 hour period to get things done. Then you will be ready for the whole day or the whole week. I have to do it like 3 times a week to keep myself healthy. So it's been working anyway. So Monday is crazy. So I cannot handle like another day on the week during the week on Thursday. If I stay for the whole day, I'm not supposed to do that as well. So I'm not paid to do that. So Thursday are OTAs. So that brings up the issue, which is now the TAs will teach the same thing, and sometimes the TA don't cover all the materials need to be covered. So I have to spend the time in the lecture to go through that, so you guys are ready for the submission tonight. Okay, and also I will cover Lab 4 as well. I will go through the template I'm going to provide with you guys. It's not a full code, but I deleted, like last time, I deleted some of the sections and give you a template. I'll show it over here, but I'm not posting the template to my website. You will watch the video and pause and do it, okay? I don't want to make it too easy. That's not right. So you guys will still type it up in your MATLAB interface. So any questions here before I move forward? So let's see the first one. If you can open up the specs of the datasheet of the speaker, it should be straightforward. Any question on this? So this is recorded. If you look at, if you watch the video, you can see that this is the highest amplitude of or volume, right? Which is at 5.3 kilohertz, and the lowest. I think what this question is talking about is the lowest sound that people can hear is 70 dB, right? So if you look at 70 dB is over here, and that will be it's called like bandwidth or the range of the frequency that we can hear, right? So anything out of the range, if you play to the speaker, you won't be able to hear. That's it for the first two questions. And moving forward, we'll bring up another interesting topic I want to talk about really briefly. Don't want to take too much time. So I showed this during section 1, but for other sections you probably didn't hear that. So see, this is a low pass filter, right? How could you tell it's a low pass?
Resistor before capacitor.
Yeah, resistor before capacitor. So resistor will be able to pass low frequency, right? DC voltage is not getting attenuated by this, right? Because it's going to be stabilized over here. So for this one, it's different. This one is different. So this component on the board, this is the audio amplifier. So this one removes DC offside. Have you heard about that before? DC offside. It's like a signal swinging around a DC value. Right? So this is 0 volts, for example. This is voltage, this is time. And if you have designed an amplifier to amplify any analog signal from the environment, it can be anything, temperature, sound, anything. So there will be most of the time, almost like 9% of the time, there will be a DC offset that you can measure. You will measure from your, you'll see it if you probe it. Okay, and your signal, which carries information, will swing around that DC offset. So sometimes, or most of the time, you don't need it. Why? Because when you amplify the whole thing, this DC offset will be amplified as well. If you amplify the whole signal by, for example, this is a top rail, like 5 volts. That's the maximum voltage you can provide to the circuit. All right. If you amplify this by twice, your DC offset will be here. And you are trying to amplify your signal as well by twice, and it's gonna swing. So top end will be saturated. This is your top rail. Nothing can go beyond that. That's the highest voltage you can provide on the circuit. So what's happening is it's gonna limit the range that you can amplify your signal that carries information. The DC offset doesn't carry information at all. Could you understand that point? DC offset, just the DC voltage, right? You'll hear the noise. For example, if I turn on some of the speakers, you'll hear like this, right? That's something. That's not a signal. It's an amplitude, but it's a DC amplitude which doesn't carry any information. However, if someone start talking, so you can hear that kind of sound in addition to that big noise, right? Well, still that DC noise is still over there. So in practice, actually, So you need to remove that DC offset in front of the amplifier, which is this capacitor. Capacitor will be able to remove DC, the low frequency components, right? So the low frequency components, like the DC offset, will be removed by this cap. So this one and the resistor forms a high pass filter. High pass filter is a high frequency, like you're talking, the sound, the volume of the music will be able to pass this high pass filter and arrive the input terminal of the audio amplifier. Okay, will be amplified. So now here's the option. There are also some high frequency noise. You wanna filter it out by using this low pass filter. But you can see these 2 points, pre and pre. If I label it as pre, the same name in Ego PCB in the schematic, so physically they will be shorted in the PCB layout. Just let you guys know. If you have done that before, you'll know that I don't have to physically wire them up. They will be shorted on the PCB layout. Just trying to simplify things because you have so many connections, like these ones as well. You don't want to directly just connect every 2 points with the wires. You'll see like millions of wires in the schematic. Super messy. So that's why we want to use labels, just names, to show that they are actually shorted to each other, like RC1, right? So you'll see RC1 somewhere else, so indicates that they are shorted. And for this one, they are shorted, so which means the low pass filter directly has an input, directly connected to the audio amplifier. And if you put a jumper here, does that make sense? Here, that's the 2 mil headers on the PCB board, and they are not shorted to each other. You put a jumper on the top, you short it. But before you do that, they are not shorted. Okay? So but this one is already connected to here. When you are using doing the lab, I don't think we used this low pass filter. So what you guys did was actually using a cable, right? So it's a female to female jumping wire, not a jumper, jumping wire. You connected the output from the microcontroller, which is a timer controlled frequency, whatever, the speaker input or the music output. You directly plug it. Remember, you're plugging a jumper onto one of the header pins around that little microcontroller, and you put the other end of the female header, the jumper to where? Remember? To amp in, right? To here. So where is this guy? Let me know in the schematic. Where is it? Where is it? Here? Here or here? Here, right? Yeah, that's what you did. Okay? Why? Because this is the header pin. This is originally internally shorted. You are not controlling anything here. So this is the pin header. You plug into here, so it's connected to the audio amplifier. If you connect to here, does it do anything? No. It's not going to send any signal to the audio amplifier. Okay? But do you need to short these 2 pins? If you don't use the low pass filter, you don't have to. However, if I short these 2 pins, I still want to hear something from the speaker. What should I do? Connect to where? LPF in, right? To here. Okay? Does that make sense? Yeah. Okay. So if you open up so the question here is very simple. You just turn, I think it's over here. I showed you here, right? Okay. So inside the schematic, it has a high pass filter outside of the audio amplifier. See this high pass filter outside of the pin 4, right? If you go to this chip, this is already outside of the chip. Okay, so I think whoever designed the schematic already look at the typical connection for this chip, already put a high pass filter over here, right? So this high pass filter is the high pass filter over here. Okay, so now you know the solution for that question. Explain itself. Okay, so this is the other terminal is not doing anything, just providing a DC offset over here. Let's come back to this. Look for schematic and layouts. The 6 screen, yeah, this is same thing. Okay. So look at schematic. In this class, in the past, people have been doing a course project. So in this class, I'm going to announce the course project, just a concept for now. So you have enough time to prepare for that. I haven't done that yet, so I don't know how much time it's going to take for me to finish it. If we do anything with Arduinos, I can get it done probably in a day. However, for PICs, I don't have the libraries. So for I2C, there's the I2C connector pin, but I don't know how long it's going to take for me to write, or if I can find it online, that'll be easier. But however, if I have to write it up, it's going to take a longer time to get it done. So what we are trying to do is get a newer version of the board, even though maybe Dr. Carlson don't want to use it anyway. We'll just add another module to it. So why is that is important, and why it's good for you guys to do? Let me explain that. If you have questions or have new ideas, let me know, okay? But now, what I'm thinking is, since only like 2 students in this class are taking PCB class, right? So I realize that you guys have career days, and I'm pretty sure a lot of people are pursuing like embedded system positions, and they will ask you PCB questions. So for embedded systems, it doesn't matter like how much time you spend on one code. You know what I mean? Like I work with like the speaker. I work on that project for like 2 months, and I get it done. I don't think that really matters. It does matter, but doesn't matter that much. So what matters during the interview is how many different types of projects you have worked on, like how many peripherals you have used, like sensors, display modules, and all the kind of things. That really makes a difference. So, and also in the PCB class, we are not building the system like this. And now the schematic is already provided. I will let you guys go through some of the PCB examples on my website. I used to have high schoolers in Durango. They went through my PCB tutorials just for 2 days. They can get a PCB out. So Eagle PC is very simple. You follow the tutorials on my website instead of the longer ones for the PCB class over here. I think you'll be able to get a PCB schematic and layout really quick. And then we will try to put all the components over here in your PCB design and place a display module like this. Okay, have a header pin so you can plug in, and a temperature sensor, either the DS. So these are the 2 temperature sensors I've used a lot. I sold the product by using this one to probe the temperature in the hot tubs. So this one is it's called one wire. I think whenever you talk about your project experience to whoever interview you, you can tell them how many different sensors have you used, how many display modules have you used, right? What are the communication protocols, things like that. So for this temperature sensor, it's very similar to I2C. It's called a one wire. It's just one single wire and 2 power and ground. It's amazing. It's one single pin sending digital data with the temperature data to the microcontroller. It's not I2C, but very similar. It's even less number of pins for I2C. Only 3 pins. Is that amazing? So power, ground, data. You couldn't have less number of pins. Power, ground. Oh, sometimes, just let you guys know, it's really interesting. Some of the fire alarm lines in the building, I haven't done that yet, but what I heard is you can run signals through the power line, so you can even save one more line. You know what I mean? Yeah. So you can run signal on power. How do you do that? You cannot run signal on ground; it's 0. But
by changing the resistance.
No, you run. It's a very tiny signal, very close, but yeah. Yes, you modulate it. You do a low pass filter. High pass filter. You filter out that DC powers. The DC power becomes a DC noise. You filter that out using a high pass filter, so you get a signal out from the power line. And anyway, so 2 lines.
Is this like a part of our class, or is this a different class? For using the
Oh, this will be the course project.
Oh.
Yeah, we have to do a course project. That's what they have been doing. It could be any project. If you tell me what you want to do, I can evaluate it and let you do it. But however, if you don't have an idea, I'm going to let you guys do the PCB. It's good for an interview in the future. So if there's is there a career fair in the spring?
Yes.
Yeah, do the PCB and just brag about it in the spring. It will make a huge difference. Even for the people who have taken the PCB class over here, they still couldn't do a system level design for the PCBs. Because I'm not allowed to do so for this semester. I was trying to do it, and I start hearing the noise. It's just one credit class. You don't want to do too much. I was trying to propose a little bit more, but again, I canceled it. So I'm not doing system level. So whatever in that class is just an analog circuit. When you are talking about like system level design embedded systems, you haven't even done a embedded system on PCB, like independent PCB, embedded system on PCB. That's not good. That doesn't sound good. So in this class, I will do it here. All right, but we'll make it simple. It's wait, where we were? Oh, the schematic. Okay, so the temperature sensor here. This is super popular from Dallas Semiconductor. One wire, very popular. You can talk about that during interviews. And there's another temperature sensor. There are just like 5 or 6 different types of temperature sensors that are popular. The reason I want to use this one is because temperature is the analog signal. So analog signal getting to the chip is being digitized by ADCs, right? And then you got a parallel digital output, and you have to convert it into a certain protocol, so you got a serial output. It's not taking a lot of pin resource on your chip. So this is just perfect because this little tiny thing looks like a transistor. It does ADC, does a protocol conversion. So the parallel digital output from ADCs will be put into a serial converter. It's being converted to a serial signal from one line, right? It's a one-liner. So you can just use one pin to receive data from it with the microcontroller. And another one takes also one pin, but you have to use it. You have to use the on-chip ADC because this is just a resistor. It changes the resistance according to the temperature change. So it's basically you are building a voltage divider. Okay, so voltage changes, temperature changes, voltage changes, and then you measure that voltage and feed it into the microcontroller. Use the microcontroller's ADC to digitize it. Okay, and then because it's within the chip, so the ADC will directly get a output and store in the register. It then directly reads to the register, and you throw it out from any output to the display module. So that can be another option. This is definitely cheaper. If you need a low cost design, you can use this one, but it's taking the ADC on your microcontroller. That's a drawback of it. If you want to use the ADC for something else, it's already taken. However, you got more channels, more than one channels of ADC.
What's the ADC? Can you explain that?
Oh, analog to digital converter.
Oh, okay.
So the analog voltage is one wire, right? It's voltage pin, one wire, and it's being digitized. Eventually converted into a digital signal, usually like 8-bit, 10 bits, 12 bits. So 8-bit ADCs are usually the very fundamental ones for the microcontroller, like Arduinos, and 10 bits is really pretty good. So 12 bits will be precision, considered as precision ADCs. So we will add a module. So first you have to build the same board, right? It's called reverse engineer. Don't sell it anyway. Probably he patented it, I don't know. So we are going to build this one and convert it to layout and identify the pins we want to use for the display and the temperature sensor, okay, and make it available on the board. So eventually what we are getting is a similar board, but there will be a space, right, having a display module and temperature sensor over there, and we'll provide the code with.
So you're talking about like designing our own PCB and like implementing the new thing. Are we actually, once we implement it, are we actually gonna like make it from there and actually like get a new board out of this, or are we
solder?
just designing?
Yeah, solder it. Yeah, let's solder it. Do you know how to solder? Yeah? Yeah, not too many components. This is not too many. This is a tiny board. We can do it quickly. I can get it done in 3 hours, I think. I'll teach you how to do it. Especially for the surface mount components, you tell them, during the interview, you tell them like you have used. That's what I want to say, right? So if they want to ask you any like project experience, you have never handled any surface mount components, that's not good. So these ones are pretty big, even though you consider them as tiny, but they are huge. It's I think it's called like 1206 in terms of the package. I don't want to spend too much time on it, but let's talk about this really quick. So this is 1206. It's a package name. So what that means is like 0.12 inch by 0.06 inches. So that's the dimension of the chip, of the resistor. I think by scale it's about this big. You can look at your board, you can tell like this big. But the ones I usually use is 0.03. It's 0.06 inches by 0.03 inches. That's the smallest one my finger can handle. So the next level one I think is, I even forgot the name. So it's, you don't want to handle anything smaller than that. That's the smallest that I can handle. So the another level down, like smaller than this, you place it on the table, you look at somewhere else, you couldn't find it when you look back. So that's not very good. This is still doable. So that's usually what I use. It can still save a lot of space, but the one being used for this board is too big to me. I usually don't sell product with these transistors, these resistors. But it's good for you guys as beginners to solder these ones. It's super simple to solder. I'll teach you how to do it. Use the irons to solder these resistors on it. And also for the chip as well. This is the surface mount microcontroller. And the pins, how to solder this, right, on the board. Not too bad at all. We'll see if we can do it, okay? But that's a goal. If you have better ideas, let me know. Otherwise, we'll just go for it and do it. So it's gonna take, we'll see. One of the labs probably will just work on the PCB instead of anything else. Okay, like I said, I think they care about how many different types of projects you have worked on instead of just working on the timers. It's just timers for the whole semester. I'm already tired with it. Don't want to deal with timers anymore, but there are still a lot of labs with timers. Okay, now let's keep moving forward with questions over here real quick. T1 Kong, right? T1 Kong, to do all these functionalities, turn it on, right? Find out T1 Kong. I showed you last time, but let's repeat it really quick. I'm doing this really quick, okay? T1 Kong, right? So first you want to turn it on. So here's the T1 TX-Con T1 Kong register. This is on, right? So look at the lowest bit over here. You give it 1, you turn it on, you enable it. Okay? And then look at this one. CS. What you want to do is this one. So FOSC, that's a crystal oscillator on board. It's 64 megahertz. And this one is being divided by 4, providing that 60 megahertz for our CPU. Okay, just to let you guys know. What's that?
Why are we looking at the lab right now, like the in-lab portions, like question 5?
Because it's due tonight.
But we did it in lab.
Oh, yeah, I know you did already. Yeah, but I just want to do it real quick.
Okay.
Yeah, but good point. So you don't need it?
I don't think so.
You already done?
Yeah.
I know we did it. We did it already, right? We did it, but we didn't finish it. Okay, let's do the more important one first, and then we come back here if we still have time. Okay? Okay. Thank you for that. It's good feedback. Now let's look at this one. I know a lot of students still have questions for the questions in the in-lab, but no worries. I think he's right. We should give higher priority to this one. Then we'll come back to the in-lab questions so we can help everyone. Okay? Make sense? All right. So now let's see this one first. This guy. Okay? Here's this first. I think that makes sense because we want to hear it first so we know what we want to program it, right? Okay, so you play the song first. If you don't press the key, the song is not playing. Keep in mind, that's something you have to program into the chip. Okay, so the next step will be you press another key, it plays the copy sound which is shorter, and then it asks you to copy that certain duration, and you'll give a tolerance in the code. If the duration you press the keys to copy the sound within that duration plus the tolerance, then it's gonna play a successful song or tell you it's successful. Otherwise, it tells you you failed. Okay. So now let's go to the next step. So it's gonna be a different key. That's the copy sound. You press the key, it plays the copy sound. And you want to copy that by pressing keys within that certain durations. Okay, that's a successful sound. So which means shows you the duration was close enough to whatever the copy sound is. Okay. All right. Make sense? So you know what are expected?
The keys you press to like copy the sound, is that the button on the board?
Yeah.
Or
Button on the board, yeah.
and it's just one button for all the.
Yes. Yeah. All right. So it's hard. That's why we have to talk about it, right? Okay. Now, 2 timers, which makes sense since we use the 1 timer. Timer 1 plays the notes, and timer 2 plays the durations. Why do we have to do that? Because they have different frequencies, right? So play the notes, it's oscillating very quickly to give you that note, certain note or scale. However, the durations are usually pretty long because you hear that a note lasts sometimes or usually for like a second. So you have to use a different timer which has a different prescaler. So that's why we set up this one to be like 1 to 256. Okay, a prescaler, so we can slow it down so it doesn't overflow too frequently. So what happens is the 2 timers are being so the 2 interrupt routines are being you get into the interrupt routines if you set it up. If you turn it on, it will start doing this. So sound like it's out of control because it's getting into here all the time and playing the notes, right? Or it's getting into here all the time playing the duration, even though it takes longer time to get into the timer 0 interrupt routine. However, during the video, remember, if I don't press any key, it's not playing. Even though I'm playing it, I still have different modes. For example, during the copy song mode, it directly plays a copy song. Or whenever I'm trying to copy it, I press it. Before I press it, it's not playing it. It's not playing anything. However, the interrupts are independent to all the other code. They will get into these interrupts. If you set it up, for example, at 4 milliseconds, it's going to trigger, turn on the flag, and get into here, right? Same for the timer 0. When timer is up, it triggers it, turns on the flag, and get into the interrupt routine, ISR. So we have to add another layer of control. Otherwise, get into it and always play it. What's that?
So is there 2 interrupt service routines,
Yeah.
one for each timer?
Yeah.
Okay.
But does that matter? That's another good question. So does that matter? I mean, one is playing, another interrupts the other one. They all happens really quickly, right? It takes pretty long to make it happen. However, when it happens, only takes like several milliseconds or even microseconds. You couldn't tell. Even though it's getting interrupted, after that interrupt is done, it will come back to keep running the original one. Same to the main C code as well. Whenever it's getting interrupted, it comes in here, run it. You know, if this one happens during this process, it runs it as well. Okay? So it's like 2 interrupt routines. You have your main code running here, right? You got 2 interrupt routines. One takes longer to trigger, another one takes shorter to trigger. It's like do the duration. This is quicker. Come back and do the playing. So the thing is, if the duration, if timer 0 is not, if you are not getting to time 0, this one triggered, you don't want to play any notes. So you get into here first. So this is playing song to be true. This is another layer of control I talk about. And you get into the next state. I'm going to talk about the state very quick, okay? No worries. So this one, move to the next state. Then you set up playing note to be true. So then whenever it's the faster ISR get triggered, you get this another layer of control to be true. So it's able to play the note. Did you get that? So this play song has to be true first. So get into timer zero's ISR. It's confusing, right? You have two control flags in this code. One is called play song, another is called play notes. If playing song is not true, it doesn't make sense to do the play notes. That's the logic or the design for the code, right? So play song to be true first, which is being controlled on the top. So it's one of the keys. Forget about this long code for now. I'm gonna zoom it out so you can see the code, so you can type it up on your end, all right? So for example, we know that you press the key, right? And you press that key, a command on the board, and you let the microcontroller to set a true to playing song, right? So playing song becomes true, all right? That's the starting point, okay? Why I can get into here? Interrupt. It interrupts. Okay? So you can always get here, no matter what. Make sense? If that key has been pressed, so the flag, which is called playing song, becomes true. Okay? Make sense? Don't get scared. We just got started. What's that?
So if you open the program and it's gonna play the song right away?
No, if you don't press the key, you press the key, you give a command, then it turns on that flag, which is playing song.
Okay.
See here? Let me introduce this concept first. Okay, it's called struct. It's a struct. So it's just defining several different states. We'll come back here later, but now you just know that these are just names, different states. So whenever it gets into interrupts, gets into timer zero, so checks the states first. So at the very beginning, it's idle, right? It's idle. So first time it gets into timer zeros in ISR, the state was idle, right? And then it's gonna check this guy. What's gonna happen? It's gonna check the flag. If you don't press anything, is the flag true or false?
False.
Okay, is it going to do anything over here? No. So after interrupts get into the time zeros ISR, what's gonna happen? What's the state? Idle. It's not changing. Where did you change the state?
Once it's true, you change the state.
Yeah, it's within that if statement, right? See? New state is signed. New state is assigned to this state variable.
Yeah.
If the playing song is not true, it's not getting into it. It's always idle. Always idle. It's gonna always break without doing anything. Okay, get into timer zero ISR, not doing anything, get out. If the ISR is not, if you are not getting into here, okay, so you are not getting into a new state, which is the next state,
Gotcha.
and the playing note won't be true. If the playing note is not true, are you going to play the note? Makes sense, right?
Yep.
That's the name of the variable. Play note. False. No, don't play it. What's that?
Then, so I'm looking at the code, right? And you have like timer zero,
Yeah.
and when you have play note equals true, and we know how we got into that state using that if statement,
Yeah,
right?
yeah.
Then how do you get into the if how do you get into the next state where play note equals false? Like there wasn't any like case that you have written where.
Oh, you press the button.
Oh, I see. So the button is.
Yeah.
Okay.
Yeah,
Gotcha.
yeah.
Gotcha.
So because it comes to the timer zero ISR only when it interrupts. Otherwise, go back to the main C code, do the scanning.
then-
So if you press, it's getting to the case,
And then it changes the state.
Change the state.
Gotcha.
right? Cool? Make sense? There? All right? Okay. So that's how it plays. So it gets into timer zero, for example, we press it. Let's just take the example, the first one we play in the video, right? Remember, let's go back to it and re-watch it really quick. That's the first time we play. So take baby steps. Get this done first. Okay? Get the 2 timers. Get this done first before we move to the copy thing. Okay? Write a song into the list with all the notes. Okay? And get 2 timers to control it. Press the key, play it. Take baby steps. Okay? How do we do it? Press the key, turn on the flag. It's gonna start doing that. Okay? So what you need to do is come back to this code and finish it. Is that difficult? No. Let's see. So this is everything you need to put on the top of the ISR, and then move to the next. Let's take a look at it. Don't change this one. Come back here, play the duration, and then move to the next state. Can you do that? How do you play the duration? Timer 0 right. Instead of timer 0, timer 0 right, the durations. Where are the durations?
Inside your matrix.
Oh yeah, that's right. Duration, see? I think this is given, right? So here's the duration matrix. What are the durations? What are the durations? The duration you want to play the note.
Yeah.
So why you want to split? Why you want to put in timer 0? It's longer, right? You play the duration. Does that matter? What does it do? It's getting to the playing duration mode, right? Okay. And what's happening?
You write to the timer, and then it's going to be shorter now for whatever duration you want. And then it goes through and.
Yeah, but just let me know what's happening in the microcontroller in parallel. What's running in parallel right now? So you write the duration, right? What's gonna happen? It's gonna wait there for delay. It's just a time delay.
Yeah.
Okay, and during that time delay, what's happening?
The notes playing.
Yes. Why?
Because you told it to.
Because play note is true.
I know you-
And because the timer 1 interrupt is faster. Okay?
I see. So turn on interrupts.
So timer 0 is doing the duration. I just set up the duration. Okay? Set up the duration.
Then you write.
Then timer 1 is not being closed because timer 1 has a play note is true. So it's going to interrupt every 4.1 second, 4.1 milliseconds. However, it's changing depending on how you write a new code into it, right? Remember we talked about that in the in-lab.
Yeah.
So during the duration, for example, 1 second, right? You got that 4 millisecond thing comes in all the time and play it. Okay? Until it's done. All right? Then move to the next state. You need to know how to assign a new state to it. How? Similar, right?
Yeah.
What's the name of the state? Play rest. What does play rest mean?
It plays a rest.
Yeah, there's a rest between notes, right?
Yeah.
Yeah?
So how do we have the play note variable? It's a bool, but it's in both interrupt routines. Is it a global variable?
It is a global variable. Yeah. It is, yeah. It's being used everywhere. It's the same. It's a flag on the top, I think. Let's take a look at it. Where is it getting defined? It's here, right? Here. It's global,
Gotcha. So it's just.
right? Cool. All right. And what's next? So move to the rest, right? Why do you want to put a false to play note? It's a rest. You are not playing the note. Make sense? What's next? Play the rest between the notes. Don't forget to increment the note index here. Where's the note index? Here, right? And play the rest. How to play the rest? Timer 0 right. Okay? You had a question?
Oh no, I didn't answer.
Okay. And then still within that, play rest. So you want to check if the note index, since you increment it over here, you want to check if it's already over the range, right? You only have like 15 notes. You want to make it larger than that. So if it's still if it's larger than that, you want to play the song still or not? Stop it because it's already over the range. Okay? And then move back to idle. Why? You are ready for the next note. Okay? If it's not over the range yet, do something else. What's the else? If not done yet, go back to where? Still play the note. It's not done yet. Play another note. Okay? So you should be able to do that. Play the first test song really quick, right? Take that baby step to get that done first. And now let's come back to the duration thing. This is hard. I don't know how students can get it done by themselves, just given like 1 week. Like at the same time taking 15 credits. So that's why I'm providing this template over here. So anyway, so you press, for example, the duration thing, like copy, right? Copy. It's like a game, right? Check if the tolerance is within that range. So that's defined by delta. So it's plus minus. It's defining that duration. So rest and the note as well. So what's happening is you are checking what? Keep thinking right now, right? So what you are checking, what you are comparing,
How long you're pressing the button for.
and the rest,
And the rest.
and the tolerance. So here is the timer 0 delay, right? Timer 0 delay, so you play the notes here, right? And there will be a rest in between the notes. Okay? So if you look at it, it's basically a note, note 1, note 2. So where's the period? What's the period? What's the one cycle? This is the one cycle, right? It's like a sine wave. You have to consider here and here. It's like this one. You have here and here. So you press it, not just the press for the duration of the note, but also the rest. You press very quickly. Still not getting your correct answer. So it has to be the note duration and the rest, and plus minus that delta over there. So that plus minus, I think you can directly use this now. I don't really care. I don't want to let you guys waste the time on testing like different tolerance, depending on your skill of the finger, how accurate that is. So I think it's using 10,000 counts. You can calculate it. 10,000 counts do what? Find out the time tolerance. This is the number of counts, right? How to find the time given the
By counts per second.
yes, divided by what?
The
16 minutes.
it's 1/256.
Yes, 16 mega divided by 256, right? It has a prescaler over there. Because the rest is being controlled by what? Which timer? Timer 0. So I have to use that timer's counts. So how to do that? It's over here provided. Still have 3 minutes. Good. Thank you, actually. I will record another video for in-lab questions right after this lecture. So for people who cannot finish the questions, you can still watch it, okay? And now let's look at it. Press R, okay? Remember, I press it, what's happening? Okay, so I press it, it plays that copy song by itself. Okay? And then I start copying it. Okay, now let's get back to the code. I press it, which is I pressed R. You have to immediately play it. Right? I pressed it, it plays it, right? So I have to assign that index copy song, which is number 2. It plays it. And then playing sound to be true, right? Because timer 0 will be engaged. And playing note will be true, become true within timer 0. So don't worry about that. Okay? While playing song, don't do anything, wait here. Whenever it's done, come out. And then disable that interrupt, timer 0 interrupt. You don't want to play it anymore, since you will start copying it. And when you copy it, timer 0 is not engaged. Because where's the timer? It's timer U, right? Timer or digger. I'm a timer or digger. I'm a timer, right? So you want to disable timer 0. Then do what? Wait until the button is pressed. You know how to do it. Like 1 equals 1, right? Something like that. Then coming here, here's another trick, okay? If the note index, which is the index of the notes, is not 0, then you want to play this. If it's 0, you want to do something else. Why? Because If it's 0, you don't have the duration yet. Because the timer, this one, keep in mind, this is another new function I want to introduce. The timer 0 read timer, what that one does is it records the current time, the current timestamp. So if you code that function, it's going to put that time as a moment over there. So whenever you do that another time, you give you another new time. If you call this function here, right, it records the duration from here to here. So if it's still not 0, you just want to directly assign timer 0 read timer to this variable. If it's already playing like node 1 or node 2, right, you can use this one to minus the previous one since it's already given in here. All right, and then you find out the duration of that, between the two timer 0 read timer thing, right? You get a duration, and you use that duration. Use this function is given, right? It's a rest and tolerance. If it works, you play this success song. If it's not, playing the fail song, right?
The fail song.
Fail song. And for the rest, it's just simple, nothing else. You need to pay attention to it. All right.